There's something quiet and strange about looking at your own hand, the skin, the lines crossing your palm, the way your fingers move when you ask them to. It looks ordinary, it feels ordinary, but beneath that familiar surface there's a story that spans billions of years and crosses distances we can barely imagine. Your hand is made of atoms, tiny particles so small that billions of them could fit on the period at the end of this sentence. And those atoms, they weren't always part of you, they weren't always part of Earth. They came from somewhere else, somewhere vast and ancient and far away. They came from stars, not the stars you see tonight when you look up at the sky. Those stars are still shining and still burning, still there. The atoms in your hand came from stars that died long before our sun was born. Stars that burned for millions or billions of years, then ended in ways both violent and quiet, scattering their contents across the emptiness of space. And somehow, across all that time and distance, those scattered pieces found their way here. Found their way into a cloud of gas that would become our solar system. Found their way into the planet we call home. Found their way into the food you ate yesterday. Into your blood. Into every cell, into your hand. We say we're made of stardust, and it's true. But what does that actually mean? Not in a poetic sense, though it is poetic, not as a metaphor, though it sounds like one. What does it mean in a real physical sense that the carbon in your bones, the iron in your blood, the calcium in your teeth, the oxygen you're breathing right now, what does it mean that all of it was once inside a star? Let's explore that together, slowly, carefully, with no rush at all, because this is a story about time, about transformation, about how the universe takes simple things and, over eons, turns them into complex things, into planets, into oceans, into life, into you. And if we follow this thread gently, if we let the ideas unfold at their own pace, something shifts. The world starts to feel different, more connected, more ancient, more impossible, and yet more real. So let's begin where all these atoms began. Not on Earth, not in our solar system, but in the hearts of stars that died before our world existed. To understand where your atoms came from, we need to think about what an atom actually is. Not in technical terms, not with formulas or diagrams, just what is it really? An atom is a tiny cluster of particles held together by forces we can't see. At the centre, there's a nucleus. Around that nucleus, in ways that aren't quite like orbits but aren't quite like anything else either, there are electrons. The nucleus itself is made of two kinds of particles, protons and neutrons. The number of protons determines what element the atom is. 1 proton and you have hydrogen. 2 protons, helium. 6 protons, carbon. 8 protons, oxygen. 26 protons, iron. Simple building blocks arranged in different numbers, creating all the different substances we know. But here's the thing. When the universe began, almost 14 billion years ago, there were almost no atoms at all. Just energy, just heat, just a kind of brightness and density we can't really picture. As the universe expanded and cooled, the simplest atoms formed. Hydrogen, mostly, some helium, a tiny bit of lithium. Those were the only elements in the early universe. No carbon, no oxygen, no nitrogen, no iron, no calcium, no phosphorus. None of the elements that make up your body or trees or oceans or planets, none of them existed yet. The universe was simple then, just vast clouds of hydrogen and helium drifting in the darkness. So where did everything else come from? Stars. Stars are the universe's workshops. The places where simple atoms are transformed into complex ones. Where hydrogen becomes helium, and helium becomes carbon, and carbon becomes oxygen, and on, building heavier and heavier elements. But this doesn't happen quickly, it doesn't happen easily, and it doesn't happen in every star. Let's think about this process. Let's watch in our minds as a star does the slow, patient work of making new atoms. Imagine a cloud of gas floating in space. Hydrogen, mostly, just simple atoms drifting. The cloud is vast, larger than our solar system, larger than we can easily picture, and it's cold. Not the cold of winter, but the cold of deep space where almost no heat exists at all. But gravity is patient. Slowly, over the thousands of years, the cloud begins to pull itself together. Atoms drift toward the center. The cloud contracts, and as it contracts, something changes. It gets warmer. Not much at first, but gravity keeps pulling, the cloud keeps shrinking, and the center keeps heating up. This goes on for a long time, maybe 100,000 years, maybe 1,000,000. The timescales involved are so long that they make human history feel like a blink. But eventually the center of this cloud becomes so hot and so dense that something remarkable happens. Hydrogen atoms start to fuse together, not because they want to, not because of any intentional plan, but because at certain temperatures and pressures, the forces that normally keep atomic nuclei apart break down. Nuclei that get close enough moving fast enough can merge. Two hydrogen nuclei fuse together, they form helium, and when they do, they release energy. A lot of energy. This is where starlight comes from, not from burning the way wood burns in a fire. Stars aren't on fire. They're doing something else entirely. They're fusing nuclei together, and that fusion releases light and heat. A star is born, and for millions or billions of years that star will do the same thing over and over, taking hydrogen, fusing it into helium, releasing energy, shining steadily into the darkness. Our sun is doing this right now, has been for about 4.5 billion years, will continue for another 5 billion or so. But the sun, and stars like it, only do the first part of the story. They make helium from hydrogen. That's it. They're not hot enough, not massive enough to do much more than that. To make the other elements, the ones your body needs, you need bigger stars. Much bigger stars. There's a pattern in the universe. The more massive a star is, the hotter it burns, and the shorter it lives. A star like our sun will shine for 10 billion years or so. But a star 10 times more massive might only last 20 million years. A star 50 times more massive might burn out in just a few million years. The reason is simple. Bigger stars have more gravity pulling inward, which means they need more energy pushing outward to stay balanced. And to generate that energy, they burn their fuel much faster. But they also do something else, something crucial. They get hot enough to fuse heavier elements. Let's watch this happen. Slowly. Step by step. A massive star begins its life the same way all stars do. Fusing hydrogen into helium in its core. But it's so hot and the pressure is so intense that it runs through its hydrogen supply much faster than a smaller star would. Eventually, after a few million years perhaps, the core runs out of hydrogen. All that's left is helium. In a smaller star, this would be the end. The fusion would stop, the star would begin to fade. But in a massive star, something different happens. The core contracts, gets denser, gets hotter, and when it crosses a certain threshold, the helium itself begins to fuse. 3 helium nuclei come together, they form carbon. Think about that for a moment. The carbon in your body, the carbon in every living thing on Earth, was made inside stars like this. 3 helium atoms pressed together by unimaginable heat and pressure, becoming something new, and the process doesn't stop there. The star keeps burning. Helium fuses into carbon. Carbon fuses with helium to make oxygen. Carbon fuses with carbon to make heavier elements. Neon, magnesium, silicon. Each new fusion process requires higher temperatures than the last, and each one produces less energy than the one before it. The star is running faster and faster just to stay balanced. In its core, layers begin to form, like an onion, an outer shell burning hydrogen. A shell below that burning helium, below that carbon, then oxygen, then silicon. Each layer burns for less time than the one before it. The hydrogen shell might burn for millions of years. The silicon shell might burn for just a day. And at the center, the core grows heavier and heavier, denser and denser, until finally the core is made of iron. Iron is special, not because it's rare. It's actually one of the more common elements in the universe thanks to stars, but it's special because of where it sits on the periodic table. Iron is right at the boundary. If you fuse lighter elements together, up to iron, you get energy out. That's what stars have been doing. That's what powers them. But if you try to fuse iron into something heavier, you don't get energy out. You have to put energy in. This means that once a star's core is made of iron, fusion can't help it anymore. There's no more energy to be gained, no more fuel to burn. The core just sits there getting heavier. And then, very suddenly, it collapses. Imagine the center of a star. A core about the size of Earth, but containing more mass than our entire sun. It's been held up by the pressure of fusion, by the outward push of heat and light. But now that pressure is gone, gravity takes over, the core collapses. Not over millions of years, not over days. In about a second, maybe less, the core falls inward. The atoms themselves are crushed. Electrons and protons merge into neutrons. The matter becomes so dense that a teaspoon of it would weigh more than a mountain. This collapse releases an enormous amount of energy. An amount that's hard to describe, hard to even think about. In that brief moment, the collapsing core releases more energy than 1 trillion suns. And that energy does two things. First, it blows the rest of the star apart. The outer layers, which have been falling inward toward the collapsing core, suddenly hit a wall of energy rushing outward. They bounce back. They are thrown into space at a significant fraction of the speed of light. The star becomes a supernova. For a few weeks it shines brighter than an entire galaxy. And second, in that moment of impossible heat and pressure, in the shockwave of the explosion, something remarkable happens. Elements heavier than iron are created. All that energy, all that intensity is enough to fuse atoms together even though it doesn't release energy. It takes energy to make these atoms, but there's so much energy available in a supernova that it doesn't matter. Gold, silver, platinum, uranium, all the heaviest elements, the ones stars can't make through normal fusion, are made in the chaos of these explosions. And then all of it, everything the star spent millions of years creating, is scattered into space. Picture it, if you can. A shockwave of gas and dust expanding outward from where the star used to be, moving fast, carrying with it all the elements that star created. Carbon and oxygen and nitrogen and iron and calcium and all the rest. The cloud expands for thousands of years, tens of thousands. It mixes with other clouds of gas, the simple hydrogen and helium that fills the space between stars. Eventually it slows down, cools down, becomes part of the general background of matter drifting in the galaxy, and there it sits, waiting. Our galaxy is full of clouds like this, remnants of ancient stars mixed together, drifting in the darkness. Some of these clouds are so old that the stars they came from died billions of years ago. We'll never know what those stars looked like. We'll never know exactly when they exploded, but their atoms remain. And sometimes one of these clouds begins to collapse again. Gravity pulls it together, and the cycle begins anew. But this time the cloud isn't just hydrogen and helium. It has all those other elements mixed in, the heavy elements from previous generations of stars. And that changes everything. About 4.5 billion years ago, something disturbed the cloud of gas and dust in our galaxy. Maybe a nearby star exploded, sending a shockwave through the region. Maybe the cloud just reached a point where gravity took over on its own. We don't know exactly what triggered it, but the cloud began to collapse. Most of the mass fell toward the centre, heating up, eventually forming our sun, but not all of it. Some of the gas and dust formed a disk around the young sun, a flat spinning disk of material, and within that disk, particles began to stick together. Dust grains collided and clumped. Clumps grew into pebbles, pebbles into rocks, rocks into boulders, boulders into mountains, mountains into worlds. The planets formed. And here's the thing, here's what matters for our story. That disk of gas and dust wasn't just hydrogen and helium, it contained all the heavy elements from previous generations of stars. Carbon, oxygen, silicon, iron, magnesium, calcium, all of it. Earth formed from that material, from the remnants of dead stars mixed together, pulled into a ball by gravity. Your planet is made of stardust. Not metaphorically, literally. Every atom in every rock, every grain of sand, every drop of ocean water came from stars that died before our sun existed. But the story doesn't end there, because Earth wasn't always a place where you could exist. For a long time it was just a ball of hot rock, no air you could breathe, no water on the surface, no life, but the atoms were there, the ingredients were there, the carbon and oxygen and nitrogen and phosphorus and iron, all the elements life would eventually need. And over time, over hundreds of millions of years, Earth changed, cooled down, developed an atmosphere, liquid water appeared on the surface, and somewhere, in some way, we were still trying to understand those atoms organize themselves into something new, into life. Think about what life is at its most basic level. It's a pattern, a particular arrangement of atoms that can maintain itself, that can take in other atoms from the environment and use them to build copies of itself. The first life on Earth was simple. Single cells, no eyes, no brains, no complexity. Just tiny bags of chemicals that could reproduce. But those chemicals, those atoms, came from stars. The carbon in the early cells' membranes, the oxygen in the water they floated in, the iron in the proteins that helped them function. All of it came from stars that exploded billions of years before life began. And as life evolved, as it became more complex, it used more of those stellar atoms. Plants evolved that could capture sunlight and use it to build sugars from carbon dioxide and water. Animals evolved that could eat those plants and use the energy. Brains evolved, consciousness evolved. And all of it, all of the matter that makes up every living thing on Earth came from those ancient stars. Your body is a temporary arrangement of atoms, you're borrowing them for a while. The carbon in your cells was once inside a star. The iron in your blood was forged in a supernova. The calcium in your bones was scattered into space when a massive star died. Before they were part of you, those atoms might have been part of dinosaurs, or trees, or bacteria, or rocks, or seawater. And before that, they drifted through space for millions or billions of years. And after you, they'll become part of something else. The atoms don't stop. They just keep going, keep changing form, keep becoming new things. You're a chapter in a story that began in the hearts of dying stars. There's something deeply strange about this when you really sit with it. We think of ourselves as separate from the universe, as observers looking out at the stars from our small planet, as if we're here and the cosmos is there. But that's not true. Not really. You're not separate from the universe. You're not outside it looking in. You're part of it, made from it. You're a way the universe has organized some of its atoms for a brief time in a pattern that can look back at itself and wonder. The iron in your blood is the same iron that was once in a star's core, the same type of atom, the same element. There's no difference at a fundamental level. When you look at a star in the night sky, you're seeing the same process that created you. Fusion, the transformation of light elements into heavy ones. The slow building of complexity from simplicity. Every element in your body heavier than hydrogen was created inside a star or in the explosion of a star. There's no other way to make them. The universe started with hydrogen and helium, and stars are the only things that can turn those simple atoms into complex ones. This isn't a metaphor, it's not poetry, though it sounds poetic. It's physics. It's chemistry. It's the actual history of the atoms you're made of. Let's think about some of those atoms specifically. Let's follow their journey. Take a carbon atom in your hand right now, in one of the cells in your skin maybe, or in a protein in your muscles. That carbon atom was once part of a massive star, maybe 50 times more massive than our sun. The star existed maybe 6 billion years ago, long before our solar system formed. For a few million years, that carbon atom sat in the star's core, part of the fusion process, helping to generate the energy that kept the star shining. Then the star ran out of fuel. Its core collapsed. It exploded. The carbon atom was thrown into space along with everything else the star had created. It travelled through the galaxy for hundreds of millions of years, maybe billions, drifting in a cloud of gas and dust. Eventually that cloud was disturbed, began to collapse, started forming our solar system. The carbon atom ended up in the disk around the young sun. It became part of a larger particle, then a pebble, then eventually a chunk of rock that collided with the forming Earth. For billions of years it was just part of the planet. Maybe in the mantle, maybe in a rock near the surface. Moving slowly through Earth's interior as the planet's crust shifted and recycled. Maybe a few 100 million years ago, that carbon atom became part of the atmosphere. Carbon dioxide, perhaps, released by a volcano. Then a plant absorbed it, used it to build part of a leaf through photosynthesis. That plant might have lived in a forest that no longer exists, might have been eaten by an animal that's now extinct. The carbon atom has probably been part of thousands of different organisms over the last few 100 million years. Plants, animals, bacteria, breaking down and being absorbed and becoming part of something new over and over, until eventually, recently, it became part of the food you ate, and now it's part of you. That's the journey of one atom, and you have trillions upon trillions of atoms in your body, each with its own story, each with its own history stretching back billions of years. Or consider the iron in your blood. Right now in your body there are iron atoms that are part of hemoglobin molecules. These molecules travel through your bloodstream, carrying oxygen from your lungs to your cells. The iron is what binds to the oxygen, what allows the process to work. Without iron you couldn't breathe, not in any meaningful way. Oxygen would enter your lungs, but it wouldn't be transported to where it needs to go. But where did that iron come from? Iron is only made in the cores of massive stars, right at the end of their lives. It's the final element that normal fusion can create. And when the star's core becomes iron, fusion stops and the star explodes. Every iron atom in your blood was once in the core of a dying star, was part of that violent collapse, that supernova explosion, was thrown into space at incredible speed, mixed with the remnants of the star, and now it's in you, quietly doing its job, helping you breathe, completely unaware of its own history. There's something humbling about that. The oxygen you're breathing right now came from stars too. Oxygen is made when massive stars fuse helium and carbon together in their cores. It's one of the most common products of stellar fusion, which is why there's so much of it in the universe. The oxygen in Earth's atmosphere, the oxygen in the water of the oceans, the oxygen bound up in rocks and soil, all of it came from ancient stars. Every breath you take is made possible by the death of stars. Think about that for a moment. The air entering your lungs right now contains atoms that were forged in stellar furnaces billions of years ago, scattered into space when those stars died, drifted through the galaxy, eventually became part of Earth's atmosphere. And now you're breathing them in, using them to power your cells, and breathing them back out again. The atom cycle. They've been cycling for billions of years, through stars, through space, through planets, through life and back again. Nothing is truly created or destroyed at this level. Atoms just change form, change arrangement, become part of different patterns. You are one of those patterns, temporary but real, a way these atoms have organized themselves for a time. When we say we're made of stardust, we're acknowledging a connection that spans the entire history of the universe. The atoms in your body are old, much older than Earth, older than the Sun. They were present in the early generations of stars in our galaxy, billions of years ago. Those ancient stars lived and died. They created heavy elements and scattered them into space. Those elements mixed with clouds of hydrogen and helium. New stars formed from those clouds. Some of those stars died too, adding their own contributions to the mix. This happened over and over, generation after generation of stars, each one enriching the galaxy with more heavy elements. By the time our solar system formed, the gas and dust in our region of the galaxy had been through several cycles of star formation and death. It was rich in heavy elements, rich enough that rocky planets could form, rich enough that life could emerge. We exist because stars died. Not just one or two stars, but countless stars, over billions of years. Every atom in your body is a gift from those ancient suns. There's a timescale here that's worth thinking about. The universe is about 13.8 billion years old. The first stars formed maybe 100 to 200 million years after the beginning, when the universe had cooled enough for gas to collapse under gravity. Those first stars were different from stars today. They had no heavy elements at all, just hydrogen and helium. They were massive and short-lived. When they died, they scattered the first heavy elements into space. Carbon, oxygen, iron, all the elements they'd created. Those elements mixed with fresh hydrogen and helium, and a second generation of stars formed. These stars had a tiny bit of heavy elements in them, and when they died, they added more. This process repeated, each generation of stars adding to the total amount of heavy elements in the universe. By the time our Sun formed, about 4.6 billion years ago, the material it formed from had been through multiple cycles. It contained a small but crucial amount of heavy elements, about 2% by mass. The other 98% was still hydrogen and helium, but that 2% made all the difference. That's what allowed rocky planets to form. That's what made Earth possible. That's what made you possible. So when you think about where your atoms came from, you're not thinking about just one star. You're thinking about many stars, multiple generations, all contributing different elements, all dying and releasing their contents into space. Your atoms are a collective inheritance from countless stars across billions of years, and this process is still happening. Right now, all over the universe, stars are living and dying. Massive stars are fusing hydrogen into helium, helium into carbon, carbon into oxygen. Cores are collapsing, supernovae are exploding. Heavy elements are being scattered into space. New stars are forming from clouds enriched by these previous generations. New planetary systems are taking shape. And on some of those planets, maybe, life is beginning. The cycle continues. The universe continues to make itself more complex, one star at a time. Our Sun will die too eventually. Not in a supernova, it's not massive enough for that. But in about 5 billion years, it will expand into a red giant, engulf the inner planets, and then shed its outer layers into space. Those layers will carry the elements the Sun has been making. Helium mostly, since that's what the Sun produces, but also trace amounts of heavier elements from the material that originally formed it. Those atoms will mix with other clouds, will become part of new stars, new planets, maybe new life. The atoms that are currently part of you will continue their journey. They'll be here long after you're gone, long after Earth is gone, long after the Sun is gone. they'll become part of something else, some new chapter in the universe's ongoing story. There's something both humbling and comforting about this perspective. Humbling because we're not separate from the universe. We're not special in the sense of being apart from it. We're made of the same stuff as everything else. The same atoms, the same elements. We're subject to the same physical laws. But also comforting because we're deeply connected to everything. The atoms in your body have been on an incredible journey. They've been part of stars and planets and clouds and countless other things. And after you, they'll become part of countless other things. You're not alone in the universe. You're part of it, made from it, connected to all of it through this shared history, this shared material. Every person you've ever met is made of stardust. Every animal, every plant, every rock and grain of sand and drop of water. We're all made of the same thing, all connected through this vast ancient process of stellar death and rebirth. Let's think about this on a more personal level. When you hold someone's hand, you're touching atoms that came from stars. When you breathe, you're exchanging atoms that came from star. When you eat, you're incorporating atoms that came from stars. The entire biosphere of Earth is built from stellar material. The food chain, the carbon cycle, the water cycle, all of it is just atoms from ancient stars cycling through different forms. Life is a way of organizing those atoms into complex, self-sustaining patterns. But the atoms themselves are ancient. They predate life by billions of years. Your body is temporary. The pattern that is you, the specific arrangement of atoms that makes you who you are, will only last for a short time. But the atoms themselves are nearly eternal. They existed long before you. They'll exist long after. They're just passing through you, briefly taking the form called you before moving on to become something else. This might sound impersonal, but it's not. It's the opposite. It means you're part of something vast and ongoing. Your atoms have a history. They'll have a future. You're a momentary expression of matter that has been travelling through the cosmos for billions of years. Let's consider what this means for how we see ourselves. For most of human history, people saw Earth as the centre of the universe. The stars were just lights in the sky, maybe holes in a celestial sphere, but not places with physical reality like Earth. Then we learned that Earth orbits the sun, that the stars are other suns, far away, that the universe is vast beyond imagining. That was humbling. We weren't the centre, we were just one planet among many, orbiting an ordinary star in an ordinary galaxy. But now we know something else. We know that despite the vast distances, despite the seemingly unbridgeable gap between us and the stars, we're connected. We're made of star material. Our atoms came from there. We're not just on a planet orbiting a star, we're made of the products of stellar fusion and death. The connection is physical, literal, real. In a sense, we're a way that stars have become conscious of themselves. The atoms that were once fusing in stellar cores are now arranged in patterns that can think, can feel, can look up at the night sky and wonder about their own origins. That's remarkable. There's another layer to this that's worth exploring. Not all of your atoms came from the same place. They came from different stars, different supernovae scattered across different parts of the galaxy at different times. Some of the iron in your blood might have come from a star that exploded 8 billion years ago. Some of the carbon in your cells might have come from a star that exploded 5 billion years ago. The oxygen you're breathing might come from stars that died at completely different times. All of these elements, created in different places, at different times, somehow found their way to the same cloud of gas and dust that would become our solar system. That cloud was a mixture, a collection of material from hundreds or thousands of different stars all blended together. And then Earth formed from that mixture, and life emerged, and eventually you. So you're not just made of one star's death, you're made of many stars' deaths. a collective contribution from across billions of years and across vast distances. Every atom in your body has its own unique history, its own journey through the cosmos, and all of those journeys happen to converge here, in this moment, in you. Let's think about the heavier elements for a moment, the ones that are more rare, gold for instance. Every gold atom in the universe was created in extreme conditions, either in the moments during a supernova explosion or possibly in the collision of two neutron stars, which creates even more extreme conditions than a supernova. Gold is rare precisely because it's so hard to make. It requires such specific, violent conditions that it's only produced in tiny amounts compared to lighter elements. But it does get produced, and some of that gold ended up in the cloud that formed our solar system. Some of it ended up in Earth. Some of it has been mined by humans and made into jewelry, coins, electronics. Every gold ring is made of atoms that were forged in one of the most violent events in the universe. The marriage of two people symbolized by a metal that came from the death of stars. There's poetry in that, but it's not just poetry, it's physics. The same is true for all the heavy elements. Silver, platinum, uranium, thorium. All created in the dying moments of massive stars. All scattered into space. All eventually finding their way here. The rarest elements are rare because their creation requires such extreme conditions, but the fact that they exist at all, the fact that they're here on Earth, is a testament to the violence and creativity of the universe. Let's return to the question we started with. What does it mean that we're made of dead stars? We've explored the literal answer. Your atoms came from stars. They were created through fusion in stellar cores, or in the explosions of supernovae. They were scattered into space, drifted for millions or billions of years, eventually coalesced into our solar system, became part of Earth, and through the processes of geology and biology became part of you. But there's more to it than just the physics. There's a philosophical dimension, a shift in perspective. When you understand that you're made of stardust, it changes how you see yourself in relation to the universe. You're not separate from nature. You are nature. You're not separate from the cosmos. You are the cosmos, experiencing itself. The atoms in your body have been on a journey that spans the entire history of the universe. From the Big Bang to the first stars to supernovae, to gas clouds, to planets, to life, to you. And that journey doesn't end with you. The atoms will continue. They'll become part of other things. The cycle will go on. In that sense, death isn't an ending. Not for the atoms. They just change form. The pattern that is you, the specific arrangement, will dissolve, but the material itself continues. You're part of a flow that has been going on for billions of years and will continue for billions more. There's a kind of immortality in that, though not the kind humans usually think of. Your personality, your memories, your sense of self, those are patterns, and patterns can dissolve. But the atoms themselves, the material you're made of, those are nearly eternal. They've survived the death of stars. They've survived billions of years of drifting through space. They have survived the formation of planets and the emergence of life, and they'll survive the death of your current pattern. They'll become part of silly water, air. They'll be absorbed by plants, eaten by animals. They'll continue. In a very real sense, the universe doesn't lose anything when you die. It just reorganizes. The atoms that were you become something else. That might not be comforting if you're attached to the idea of you as a permanent, unchanging thing, but if you can see yourself as a temporary pattern, a brief arrangement of ancient atoms, then death becomes less frightening. You return to the universe. The atoms that borrowed your form for a while go back to the pool ready to become something new. This perspective can change how you live too. If you're made of stardust, then so is everything around you, the people you love, the places you visit, the food you eat. All of it came from the same source. All of it is part of the same cosmic story. There's a kind of kinship in that, a deep connection. You're not just related to other humans, you're related to trees, to rocks, to oceans, to stars. All made of the same stuff, all part of the same process. And if the atoms in your body have been on such a long journey, if they've been part of so many different things, then maybe the current moment deserves attention. Gratitude, even. These atoms have been cycling through the universe for billions of years, and right now, for a brief time, they're arranged in a pattern that can think and feel and experience the world. That's not permanent. It's not guaranteed. It's a temporary state, a moment in a much longer story. But it's your moment. The atoms that are you right now are having this experience, looking through your eyes, thinking your thoughts, feeling your feelings, and then they'll move on, become part of other patterns, other experiences. So maybe there's value in paying attention, in noticing the moment, in appreciating the temporary nature of this particular arrangement. You are stardust, briefly conscious of itself, and someday you'll be stardust again, unconscious, waiting to become something new. Let's think about the scale of all this. The universe has been creating heavy elements for about 13 billion years. That's a long time, long enough for multiple generations of stars to live and die. Long enough for the galaxy to become enriched with the products of all those stellar deaths. Our sun is relatively young, astronomically speaking. It formed only 4.6 billion years ago. There were already 8 or 9 billion years of stellar evolution before that. 8 or 9 billion years of stars creating elements and dying and enriching the cosmos. By the time our solar system formed, the universe had been doing this for most of its history. The material we formed from was already rich in heavy elements thanks to all those previous generations of stars. Earth is a latecomer. We're made from recycled material. Our atoms have already been through multiple cycles of star formation and death before they became part of us. That means your atoms are old, or really old. Not as old as the universe itself, but ancient by any standard we can relate to. The carbon in your body might have been created 6 billion years ago. The iron might be 7 billion years old. The oxygen might be 8 billion years old. These atoms are older than Earth, older than the Sun. They've been around for most of the history of the universe, and yet they're still here, still functioning, still part of the ongoing story. There's something deeply stable about atoms. Once created, they don't just disappear. They can be broken apart under extreme conditions, like in nuclear reactions, but under normal circumstances, atoms are essentially permanent. The iron atom in your blood today will still be an iron atom billions of years from now. It might be part of something else, somewhere else, but it will still be iron. This stability is part of why the universe can become complex. If atoms were constantly breaking apart and reforming, if they weren't stable, then nothing could build up. No planets, no life, no complexity. But atoms are still. They endure. They can be passed from one form to another, from one structure to another, without losing their fundamental identity. That's why your atoms have such a long history. They've been around since they were created in stars, and they'll continue to be around, effectively forever. You're made of matter that is, for all practical purposes, eternal. Not the pattern that is you, that's temporary. But the underlying substance, the atoms themselves, those endure. Let's consider some of the philosophical implications of all this. If we're made of stardust, then in what sense are we separate from the universe? Western philosophy has often drawn a sharp line between mind and matter, between consciousness and the physical world. There's the thinking subject, and then there's the object of thought. We're in here, and the world is out there, but the stardust perspective challenges that. The matter that makes up your brain, the neurons that generate your thoughts, that matter came from stars. There's no fundamental difference between the atoms in your head and the atoms in a rock or a star. The only difference is arrangement, organization, complexity. Your brain is a highly organized structure. It's matter that has been arranged in a specific way, a way that allows for information processing, for memory, for consciousness. But it's still matter, still made of atoms, still part of the physical universe. So consciousness isn't something separate from the material world, it's something the material world does under certain conditions. It's a property that emerges when matter is organized in particular ways. You are the universe, organized in a way that allows it to think about itself. That's not a reduction. It's not saying consciousness is just matter. It's saying consciousness is what matter does when it's arranged in certain complex patterns. And those patterns are possible because the stars died and created the elements necessary for that complexity. There's also an ecological dimension to this. If everything on Earth is made from the same pool of atoms, all derived from ancient stars, then we're all sharing the same limited resource. The carbon in your body right now might have been in a tree 100 years ago, or in the ocean, or in the air, or in another person, or in a dinosaur 65 million years ago. Atoms cycle through the biosphere. They're constantly being exchanged. Nothing is truly yours in a permanent sense. You're borrowing these atoms for a time. This creates a kind of ecological responsibility. The atoms you use will be used by others after you. The carbon you emit into the atmosphere will become part of plants or oceans or other people's bodies. We're all sharing the same limited pool of matter, all connected through this constant exchange of atoms, and those atoms are precious. They took billions of years to create. They came from the deaths of stars. They've been cycling through Earth's systems for billions of years. To waste them, to pollute them, to disrupt the cycles that have been sustaining life for billions of years, that has consequences, not just for us, but for everything that comes after. Because the atoms will continue. But the patterns they form, the ecosystems, the life, those can be disrupted. And once disrupted, they might not recover in the same way. We're all made of stardust, but we're also all sharing that stardust. All dependent on the same cycles, all connected through this ancient material that the universe spent billions of years creating. Let's think about time differently for a moment. When you look at a star in the night sky, you're seeing it as it was when the light left it. If the star is 100 light years away, you're seeing it as it was 100 years ago. For distant stars, you might be seeing light that left thousands or millions of years ago. In a sense, when you look at the night sky, you're looking back in time. You're seeing the universe's past. But there's another way to look back in time. You can look at your hand. The atoms in your hand were created in stars that lived and died billions of years ago. They've been on a journey through time and space that spans most of the universe's history. When you look at yourself, you're looking at ancient matter. You're looking at the products of stellar fusion that happened long before Earth existed. Your body is a window into the past, a physical connection to the early universe, to the first generations of stars, to billions of years of cosmic history. You carry that history with you, in every cell, in every atom. There's a kind of reverence that can come from this understanding. Not a religious reverence necessarily, but a sense of wonder, a sense of connection, a sense that something vast and ancient has led to this moment. The atoms in your body have been on an incredible journey. They have travelled across the galaxy. They've been part of stars and planets and life. They have survived unimaginable violence and unimaginable stretches of time. And now they're here, in you, allowing you to exist, allowing you to think and feel and experience the world. That's not something to take for granted. It's not something that was guaranteed. It required billions of years of stellar evolution, the death of countless stars, the formation of a planet in just the right location, the emergence of life, the evolution of complex organisms. An incredibly long chain of events, each one necessary, each one building on the last. And you're the current result. The current expression of all that history, not the final result. The atoms will continue after you, but right now, in this moment, they're arranged in the pattern called you, and that's something worth appreciating. Let's consider the future. Right now, stars are still making heavy elements. The universe is still enriching itself with the products of stellar fusion and death. In the distant future, billions of years from now, the universe will have even more heavy elements than it does now. Even more complex chemistry will be possible. Even more potential for complexity and life. But there's a limit to this process. Stars need hydrogen to burn, and while there's still a lot of hydrogen in the universe, it's finite. Eventually, over trillions of years, the universe will run out of hydrogen that can collapse into new stars. The last stars will form, will burn and will die, and then there will be no more stars, no more fusion, no more creation of heavy elements. The universe will become a cold, dark place, full of dead stars, black holes, and drifting particles. No new complexity will be possible. That's a long time from now, trillions of years, an almost incomprehensible amount of time, but it means the current era, the era of stars and galaxies and planets and life, is temporary. It's a phase in the universe's history, a phase where conditions happen to be right for complexity. We exist during this phase. We're part of this brief window when the universe is full of stars and can create the elements necessary for life. Eventually that will end, but for now, for these few trillion years, the universe is alive with possibility, and you're part of that possibility, a living expression of what the universe can do during this era. Let's come back to Earth, back to the personal. You're standing on a planet made of star material. You're breathing air made of star material. You're looking at a sky full of stars that are still making the elements that future generations of life will be made from. Everything around you has this history, this deep connection to the cosmos. The tree outside your window, the water in the ocean, the mountains in the distance, all of it came from stars. All of it is part of this vast, ongoing process. And you're not just an observer of this process. You're part of it. You're made of the same stuff. You're a continuation of the same story. When you die, your atoms will return to Earth. They'll be absorbed by soil, by water, by air. They'll become part of plants, animals, microorganisms. They'll continue to cycle through the biosphere. Maybe someday, billions of years from now, Earth will be consumed by the sun as it expands into a red giant. Your atoms will be vaporized, sent back into space. And maybe they'll drift through the galaxy again. Maybe they'll become part of a new cloud of gas. Maybe they'll help form a new star system. Maybe they'll become part of new life on a new world. The journey continues. Your atoms have already travelled so far for so long, and they'll keep going. You're just one chapter in their story, but you're a chapter. You're part of it. You matter. Not in the sense of being the centre of the universe, but in the sense of being connected to all of it. Part of the same flow, made of the same ancient material. So what does it mean that we're made of dead stars? It means we're part of the universe's long process of creating complexity from simplicity. It means the matter we're made of is ancient, far older than us, and will continue long after us. It means we're connected to everything else through this shared material, this shared history. It means the boundary between us and the universe is not as clear as we might think. We're not separate from nature. We are nature. We're not outside the cosmos looking in. We're the cosmos. Experiencing itself from within, it means death is a transformation, not an ending. The atoms continue, the patterns change. It means life is a temporary arrangement of a matter that has been travelling through the universe for billions of years. And it means this moment, right now, is part of an unimaginably long story. A story that began in the hearts of dying stars, and that will continue long after you and I are gone. You're stardust, literally, physically, in every atom. And for this brief moment, that stardust is arranged in a way that can think, can feel, can wonder about its own origins. That's remarkable. That's what it means to be made of dead stars. There's no dramatic conclusion to this story, no final revelation, no twist ending, just the slow ongoing process of matter changing form, of atoms cycling through different patterns, of the universe creating complexity, sustaining it for a while, and then letting it dissolve and reform into something new. You're part of that process, right now in this moment. The atoms that are you were forged in stellar furnaces billions of years ago. They've travelled across the galaxy. They've been part of countless other things. And now they're part of you, and someday they'll be part of something else. The cycle continues. The atoms endure. The patterns change. And for now, for this brief window, you get to experience it, to be aware of it, to look up at the stars and understand that you came from there, that you're connected to it all. That's what it means. That's what it's always meant. We're made of stars, and stars made us. And the journey continues. If you found some peace or wonder in these thoughts, if you've stayed with this exploration, thank you. These ideas, these connections between us and the cosmos, they're worth contemplating, worth returning to, worth carrying with you as you move through the world. Because when you understand that you're made of stardust, it changes things, not all at once, not dramatically, but quietly, over time. You start to see the world differently, see yourself differently, see your place in the vast sweep of cosmic history. And maybe that's enough, maybe that's all we can ask for, a shift in perspective, a deeper sense of connection, a quieter mind at peace with its place in the universe. If these thoughts have brought you any of that, then consider exploring more of these ideas. There are many questions about the cosmos, many perspectives to consider, and this channel will continue to explore them gently, without rush, in this same spirit of calm curiosity. Until then, rest well. And remember, you're made of stars. Every atom, every cell, every breath. You're the universe experiencing itself, and that's enough.